Now I would invite Prachi ma'am to start the session.
Hello everyone, good morning. How are you all?
Good.
So I think you have done with your previous class, right? So you all can interact in the chat and then we'll begin learning chemistry. Hello everyone. So yes. Hmm. So I can't see your chat actually. Yes. Okay, so I hope we have new students in the class. So we'll quickly start with knowing uh, those who are new to the class, whether they have started learning the chapter that we are doing right now in the class is atomic structure, if you know. Now, quickly tell me, have you read or have you watched the recorded session for the chapter that is the atomic structure? So the chapter that we are doing right now is atomic structure. So for the students who are new to the class, so I just want to know, like, are you reading it? So today is it your first class, or have you read or have just given a quick reading to this topic? Yes. Just give me a second because I can't see your replies, so I'll join again.
No, students, 1 second, ma'am. Students, please
Yeah.
forward your replies to Prachi ma'am.
Okay, that's why I was not able to see. Okay. So yes, just uh, I want to know, have you read this chapter before so that we can start in that way? If you haven't read it at all, then yes, our approach. Otherwise, if you have read this or know the basics of this chapter, then we will continue with the topic that we were left in the last session. So yes, you can reply to me because I can't see your replies for now. So once you give me an idea, like whether you are familiar with this topic or not, then we'll begin with whatever we were learning. Yes, good morning, everyone. Good morning to all. I hope none of you is feeling sleepy. So be active and be ready for the class. So here in atomic structure, basically, we'll be learning everything about how the atoms look like and what are the things that are there in the atom. Right? So we'll be learning about the things at the microscopic level. And here we are learning right now about the atomic models. So the topic that is going right now in the class is the atomic models. Yes, you all can send the message to me, right? So that I can see it. I think you are sending it to sir or ma'am. So what you can do is you can select there, send to, you will see the options there. So you can send the messages to me. for names there so that I know who all are there in the class. And then we can just quickly interact with each other, and then we can begin with the lesson, right? Yes, Gayatri is there. So you quickly have to type your name and then we'll begin. So by then, for the time being you are typing your name, I'll tell you what actually we are doing or learning in atomic structure right now. So right now we are learning about the atomic models. We are learning about the atomic models. So there were different models that were given according to the experiments that were being conducted at that time. So the first model that was given was the JJ given by is the JJ Thomson, which was also known as the plum pudding, raisin, or watermelon, which you have learned in lower classes also. Like your atom, he imagined it as a watermelon, or it will look like a. So the more relatable example would be watermelon for us, right? So it was the model was given by J.J. Thomson. The model was given by J.J. Thomson. So he was the one who discovered electron. He was the one who discovered electron. Now his student, that is Rutherford. His student, who was Rutherford, he gave the other model of atom, which was known as the Rutherford model of atom. So now let's take a quick look at the picture, how he imagined atom. So for the J.J. Thomson, atom would be like you will have an atom, and in that he said that we will have a positive matrix which is distributed all over the atom, and on to that we have the electrons which are embedded in this positive matrix. So this is the picture of atom according to J.J. Thomson. What about the Rutherford? So Rutherford, when he conducted his experiment, which is the gold foil experiment, he conducted the gold foil experiment where he bombarded the gold foil. He took a gold foil, he kept the detectors around it, and what he did is he bombarded it with the alpha particles. He bombarded it with the alpha particles. So I'm not getting your messages. Yes, Gayatri is there in the class. Who else is there in the class? You just type your name, and then yes, quickly we can interact. So we'll start with, you have to tell me when I say alpha particles, so what do you mean by alpha particles? Yes, Omkar is there, Gayatri is there, Bhaskar is there. Yes, we have Gayatri, Omkar, Bhaskar. So can you people tell me what are alpha particles? What are alpha particles in the gold foil experiment? So when he conducted the gold foil experiment, which we have discussed in detail, like what were the observation, and depending on the observation, he made certain conclusion. So now what were those conclusions? The conclusions was that all the positive charge, it is concentrated in a very small volume at the center of the atom, right? At the center of the atom, and then electrons revolve around this nucleus. So this nucleus, it is densely packed at the center of the atom, right? And there was and why did he give such a structure for atom? Obviously because of the observation that he made in the gold foil experiment. Now after that came the Bohr's model. Bohr's model. And then the fourth one is quantum mechanical model. Quantum mechanical model. So for the Bohr's model, yes, he just made the improvements to the Rutherford model based on the things that were going at that time. So he took Rutherford model, studied it. He studied all the experiments that were done by the other scientists, and what were the conclusions given by them. So yes, his model obviously looked similar to the Rutherford, but yes, he made significant changes to the Rutherford model. So Rutherford, basically, he was not able to explain the stability of the atom, right? So the shortcoming, or we say the drawback of the Rutherford model, was that he didn't say anything about why the electron will keep revolving around the nucleus, right? So then Bohr came with a model where he said that nucleus will be at the center, and then we will have the different energy levels, and the electrons, they will be revolving around the nucleus at a certain, in these energy levels. They can only go from one energy level to the other energy level when they emit or absorb the energy. So this is the picture of atom according to Bohr. This is the picture of atom according to Rutherford. Now, how do the atoms look like according to the quantum mechanical model? So it's like, obviously the nucleus is at the center in Rutherford, Bohr, and the quantum mechanical model. But according to quantum mechanical model, around the nucleus, the electrons, they will be present as the cloud around the nucleus. So it's like a cloud, how you see the cloud, right? So in this, we will learn that here we will not be talking about the exact position of the electron. We will be learning about what is the probability of finding the electron in a particular area. So these are the pictures of the atoms. This is how the picture of the atom it developed over centuries, right? So it took around 87 years to come to this model, which is the quantum mechanical model, which, yes, contains so many things which are observed experimentally, right? So right now, the model that we are using is the quantum mechanical model. Now, we have learned about the J.J. Thomson model, Rutherford model, and now we are on the developments. We are on the developments that led us to the Bohr's atomic model. So in that we learned about the dual nature of electromagnetic radiations, and second we will be learning about the atomic spectrum. Right? Secondly, we have to learn the atomic spectrum and all the things conditions were made by looking at atomic spectrum, and especially we will be about the atomic spectra of hydrogen, atomic hydrogen, right?
Excuse me, ma'am.
That we learned in the nature of electromagnetic.
Please wait for a few seconds, students. There is a technical issue.
Hello.
Yes, ma'am, you're
Uh,
audible now.
okay, okay. Is my voice clear now?
Yes, ma'am, your voice is clear.
Okay. Yes. Okay. So yes, who all are there in the class? We have Gayatri, Omkar, Bhaskar. What about the new students? You have to just type your name. That is it. This the only that you have to start with is just type your name in the chat. The message, you can send the messages to me, right? So yes, Gayatri, what did we learn in the dual nature of electromagnetic radiation? What were the two experiments that we learned about? Yes. So in dual nature, we said that it behaves as the wave, the radiations that are around us, right? Be it microwave, radio waves, X-ray, UV, all of them, they will take electromagnetic radiation. So the first question is, what are electromagnetic radiations? So radiations that we talk about in our daily life, right? The radiations that are coming out of our mobile phone. So there we are using the radio waves for the communications, and also we have the UV rays that are coming from the sun. We have infrared radiations which are coming from the hot bodies. Any heated object will emit the infrared radiations. So basically, IR radiations will be coming from our body, right? But they are not that strong that it will be visible to our eyes. Our eyes can't uh, catch the infrared radiations. There is a very small part of the spectrum which we can see, which is the visible light, right? Which is the visible light. Yes, we learned about that the electromagnetic radiations, they will be behaving as wave and they will be behaving as. And in particle, what were the two experiments that we learned about? Yes, we have Umar, Bhaskar, Omkar, and Gayatri. And I see there are lot many students in the sessions. So quickly type your name in the chat. I hope you are able to do that. Yes, what were the two experiments that we learned about for the particle, where we came to know by what were the experiments by which the scientists came up with the fact that the electromagnetic radiations, they will be behaving as the particle. Yes, we have Bhavna, Umar, Bhaskar, Omkar, and Gayatri. So yes, Bhavna and Omkar and Gayatri, you were there in the last classes, right? So can you quickly tell us what were the two experiments that we learned about? Yes, Gayatri, if you can unmute yourself, then yes. So what were the experiments that we learned about? So first we learned about the black body radiation. So to explain that, we learned about the Planck quantum theory. We learned about the Planck's quantum theory, and then we learned about the photoelectric effect. Right? Then we learned about the photoelectric effect, which was explained by the Einstein, and he took the help of the Planck quantum theory for that. So in the wave nature, we learned that the electromagnetic radiation, they will be like a wave. So how do I see as a wave? So wave will look something like this. How do we, and these are. Now how do I define the wavelength? Distance between my wave, you can take it or you can take it as, right? So the distance between two consecutive same points. So from one crust to the other crust, that is the wavelength of the wave, right? And then we learned about the frequency, which was denoted by nu, and also we learned about the wave number. So the frequency and wavelength, they are related as C is equals to lambda into nu, right? And how do we define frequency? Yes, quickly tell me, how do we define frequency? So do you know what frequency is? How many of you know what frequency is? Quickly type Y. So what we do in our classes, if you know the answer, you can just quickly type, simply you can type Y and then we can move ahead. Yes. So Gayatri says that the frequency is the number of waves that are passing through a particular point per second. So the more shorter is the wave, the more shorter is the wave. So the number of waves that will be passing through the particular point will be more. If the wave is longer, if the wave is longer, then the number of waves that will be passing through this point, it will be less. So for a wave with a lesser frequency, with which is shorter, that will have the more frequency, and the longer wave will have the more frequency, and the longer wave will have a less frequency, right? So yes, Bhavna says the number of waves passing through an area or a point in a unit second. So we'll write it as through a point. Through a point in a unit second is what is known as the frequency. And the wave number is simply the reciprocal of formula that we have to keep with us. Our way from there, we have got one formula, which is that the speed of light is equals to wavelength into frequency. So speed of light will be wavelength into frequency. So from here we have got lambda into nu. And what is the speed of light? We all know. What is the speed of light? Yes, everyone, you have to tell me what is the speed of light. So yes, we have other students also, right? So we have Manish, Umar, Akshay, Niharika, Gayatri, Pratyusha, Pawan, Bhavna, Akshara. So yes, what you have to do is make sure that you are interacting in the chat, right? Yes, we all know that the speed of light is 3 into 10 raised to the power 8 meter per second. So this is just a quick recall for all the people who have not started with this unit. So this is how, this is the roadmap of the chapter that we started with the atomic model, and right now we are learning about the developments which led to the Bohr's atomic model. And in that we started with the dual nature of electromagnetic radiation, in which we learned that it behaves as a wave. So whenever your radiations, they are traveling in the space, they will be traveling as a wave. This was the observation, right? Where we know that the speed of these waves, the speed with which these radiations will travel, it will be equals to the wavelength into the frequency of that particular wave, where we know that all of them, they will be traveling with the speed of 3 into 10 raised to the power 8 meter per second. So your light will consist of so many radiation, which we will see what are the radiations, right? So these are the radiations that the light will consist of, which ranges from radio waves to gamma waves. And the important part for us is there is just a small part of the radiation which we can perceive with our eyes. Rest of it we can't see with our eyes. We have to use a specific instrument to catch these waves, right? So this is the whole spectrum. So the light that is coming from the sun, it will consist of so many radiation, but we just see the small part, right? We just perceive the small part. That is this is Vibgyor, which you all have learned in your lower classes, right? It consists of, Vibgyor is just, it's a spectrum of color which we can perceive with our own eyes. Now the other question that is important for you is, what is the range of the visible light in the spectrum? right? So it is from 750 nanometer to 400 nanometer. So you can get a direct question from here that the visible part, it ranges from 750 nanometer to 400 nanometer. Now what you can observe here, tell me. So if I am going from radio waves to the gamma waves, what is the observation? Is the frequency increasing or is it decreasing? So when I'll move from radio, then we are going to radio, micro, infrared, then we have the visible part, ultraviolet, X-ray and gamma rays. So when I am going from radio waves to gamma rays, what you can see? Is the frequency increasing or it is decreasing? Or let's start with the wavelength. What do you see? Is the length of the wave increasing or is it decreasing? Just you have to do your observation, right? The spectrum is in front of you. Look at the wave and decide what you can see. Is the wavelength increasing or is it decreasing? Yes, the wavelength, the length of the wave, what you can see. Yes. What about others? Yes, Bhavna says the wavelength is decreasing. Gayatri says the wavelength is decreasing, frequency is increasing. All of you have to interact. You have to put the answers in the chat. The interaction is very important. It's a quick revision for you. And by that, I'll also know whether you know the particular things or not. So what is happening here is that as I am moving from the radio to the gamma rays, then what is happening here is that the length of the wave, it is decreasing. So wavelength, it is decreasing and the frequency is increasing. So the frequency is increasing and later on we'll see how did the Planck, he related this energy with the frequency. So right now you must know that the energy is increasing as we are moving from the radio to the gamma radiation. So you should know the sequence. So first we have radio waves, then we have radio, micro, infrared, ultraviolet. In this, between the infrared, which we say IR radiations, so infrared can also be said as IR radiations. So in between of infrared and the ultraviolet, we have the visible part, and then we have X-ray and gamma. This is the whole spectrum of which all people there is just a small your eyes, which is this part, right? And as you can see, this is a very small part of the so this kind of right. And what is said about these radiations that we as a wave, we will learn that they will be traveling at
Voice
the
is
speed
cracking.
of this much. That's how the wavelength and the frequency is. Okay. Just give me a second, ma'am. I'll hello.
Yes, ma'am. Now it's fine.
Okay.
Yes, ma'am.
Hmm. So now then we moved on to that what were those experiments by which this scientific community they came up with the conclusion that your radiations they have particle nature also. So in that we learned about two things, which is the black body radiation and the photoelectric effect. So black body radiation is basically, you might have observed that when we are heating something, so as we change the temperature, the color of the object, it changes, right? So where did this word came from, which is the black body radiation? So what is said is that the black body will be something or any object which can absorb all the radiation and also it can give out all the radiation. For example, the example of black body around us is sun, the stars that you see. What they are doing is they are emitting all kind of radiations, right? Stars, be it stars or sun, they are radiating all kind of radiations. So they are the example of the black body. And yes, the objects that we heat, they are also the examples of the black body. Let's suppose if I take a iron rod, correct? And I start heating it. So what I will see is that initially it will be light red. Initially it will be light red. Then the color becomes darker. Then the color it changes. From red it goes to yellow. From red it goes to yellow. From yellow it will become white and then it will become blue. So that's how the color will change. And for this, the plot that they were getting is, here we have intensity of light and here we have the wavelength. So this is the plot that they were getting, that for the particular temperature we have the particular wavelength, the maximum wavelength, right? And what was expected is, they were expecting the graph to be something like this, which is different from their expectation. So none of the scientists, they were able to explain these plots when they were considering radiations as wave. Then Planck came with a hypothesis. Planck, he came with the hypothesis that the light, instead of coming as a wave, it is coming in a packets. How it is coming? It is coming in the packets. And each packet will be known as, yes, you have to quickly tell me in the chat, the each packet of light, it will be known as, yes, Gayatri, Bhavna and Omkar and those who all were there in the class last time. Yes, each packet of light will be known as quantum of light or quanta of light or photons. So what he said is that the light, it will be coming in the packets. It will be coming in the packets. And how did he give the energy of these quantums? He gave that one quantum will be equals to the energy of one quantum. It will be proportional to frequency. And then he gave the formula E is equals to h nu, where h is the Planck's constant. H is the Planck's constant. And what is the value for the Planck's constant? 6.626 into 10 raised to the power minus 34 joule second. So this is the next formula that we have got out when we are learning about the particle nature of the electromagnetic radiation. So the Planck gave us the formula which we will be using throughout the chapter now. That is, energy is equals to h nu. Now the other way of writing it is, E is equals to Hc over lambda. Because now we know the relationship between C is equals to lambda into nu. Now here from here I can find out what is nu. Nu will be is equals to C over lambda. So depending upon what you are given, whether you are given frequency in the question or whether you are given the wavelength, you can use the appropriate formula. Now the other important part is the units. What the other important part is unit. You have to take care of the units that are given for the wavelength. So it may be given in meter, centimeter, angstrom or picometer. Now what should be the power? So if I write 1 angstrom is equals to dash meter, 10 raised to the power minus x. So what should be the value of x here? And you have to quickly tell me for the value of y also. So what should be the value of x and what should be the value of y? How is angstrom related to meter and how is picometer related to meter? Yes. So Omkar says that your value of x here will be 10. And what should be the value of y? Yes. Yes. For angstrom, it is 10. And for picometer, do you know what's the value for picometer? Yes, it is 12. Now quickly tell me what will be the relationship between angstrom and picometer. What should be the power of 10? Because yes, in the numericals, you may be required to convert the angstrom to picometer or picometer to angstrom. Now you have to quickly calculate this because now you know how both of them are related to meter. You know how these both are related to meter. Picometer is also a unit for measuring the length, right? Because the atoms, they are very, very small. So we have to use the smaller units. For example, angstrom, centimeter, picometer, millimeter, micrometer. Because the atom is very, very small. So yes, for measuring the distances between the atoms, we will have to use a smaller unit, and one such unit is picometer. And all of these we have learned in the basic concepts of chemistry, right? How are the smaller units? They are related to the larger units. Yes. So here what we will get, we'll get it as 2. You have to keep this with you because yes, obviously we'll be using this in the formulas, in the numericals. So this is what we have got out of Planck's quantum theory, which is we have got how do we calculate the energy? How do we calculate the energy? Now how the story goes. So yes, Planck was able to explain this plot. Which plot? This plot. And yes, of course, we don't have to go into the details of these plots or what were the formulas that were given. We are not supposed to understand what was the mathematics or the mathematical formula that he gave for this, so that he gets the same plots for the from the whatever formula he gave. What he did was he kept the values and he did a plot. What he observed is, yes, he got the same plot what was being observed through the experiments. But the main gist of the formula was that he considered light as a particle, where he said that the energy will be proportional to the frequency. And the formula which is important for us is this one, which is the energy is equals to h nu. Our takeaway is the value for the energy and the Planck's constant, right? Now then, after that, we learned about the photoelectric effect, right? After that, we learned about the photoelectric effect. So, what did we learn in the photoelectric effect? Yes, what did we learn in the photoelectric effect? Do you remember that? So, the experiment, it was performed by Hertz, right? The experiment, it was performed by Hertz. So what he did is he radiated light on a metal surface. He radiated light on the metal surface, and once he radiated the light on the metal surface, what was observed is that there is ejection of electron. Yes, Bhuvneshwari says there is ejection of electrons from the metal surface. How would we know that their electrons are ejected? Because we'll see that some current starts flowing into the circuit, right? The current starts flowing into the circuit. Now, what he did is he changed the light, he changed the metal, and there were certain observations that he made. There were certain observations that he made. So, what he observed is that there is a certain minimum frequency that will be required for the ejection of electrons. So let's suppose this is a metal, this is sodium, right? Let's suppose this is potassium. Let's suppose this is potassium. So what he did is when he radiated red light, when he radiated red light, there was no ejection of electrons. And then what he did is he said, okay, I am not able to get any electrons when I am keeping the intensity less. So what he did is then he increased the intensity. Then he increased the intensity of light. Still there was no ejection of electrons. Now, after that, the question that he came to his mind is, okay, I am not able to get the current by radiating the red light. Let's try with the yellow light. So first he tried with very dim yellow light. And then as soon as the light strikes the metal surface, there was the ejection of electrons from the surface. And the next thing that he did is he increased the intensity of these radiation. What he did is he increased the intensity of these radiation. And what changed after increasing the intensity? What will happen if I'll change? You can take any other light also, Bhuvneshwari. He might have tried with all the lights, right? Whatever you see in Vibgyor. Correct? He tried with red, orange, yellow. Then when he came to yellow, he observed that there is ejection of electrons. So we are looking at the conclusion, right? So yes, of course, he might have tried all the colors and he has put his observation. So now when he increased the intensity of the yellow light, what will change? So yes, this we have learned yesterday. So quickly, all who were there in the class, you have to tell me what will happen if I increase the intensity of the yellow light. What will change if I change the intensity? What will change if I change the intensity? Yes, Gayatri, Bhavna, Omkar, what will change if I change the intensity of the light? So if I change the intensity of the light, then what will happen is, let's suppose only two electrons were emitted when I had a very dim yellow light. Now if I increase the intensity, then yes, the electrons, the number of electrons that will be coming out of the metal surface, it will increase. Now earlier when the light was dim, two electrons were ejected. Now if I increase the intensity, the number of electrons that will be coming out will increase, and in turn that will increase the photo current. That will increase the photo current. The current that is because of these electrons which are ejecting because of the radiation of light. And light, as Planck said, photons. That's why we say them as photoelectrons, right? He said that quanta of light or photons. One packet, it will be one photon. Correct? So that was his observation, that your number of electrons that are coming out, number of electrons ejected, they are proportional to the intensity of light. They are proportional to the intensity, or in the simpler words, what I'll say, brightness. What I'll say, brightness of light, right? Now, the other thing that he observed is that as we are increasing the frequency. Now what he did is, yes, for yellow light, electrons, they started ejecting, and as I was increasing the intensity, the number of electrons, uh, the number of electrons that were ejected, they increases. But when he took the light of the higher intensity, let's suppose he took the violet light or the blue light, then what has happened is, the electrons, they were coming with a higher speed. The electrons that were coming out, they were moving with the higher speed. So from that he concluded that kinetic energy is, from that they said that kinetic energy will be proportional to the frequency, but it will not be proportional to the intensity. Whether I increase the intensity or I decrease the intensity, if we are not providing the minimum frequency which is required for the ejection of electrons, then no electrons, photoelectrons, will be emitted from the metal surface. Right? So this is what they have done in the photoelectric effect. So the minimum frequency that will be required for the ejection of electrons is known as, so quickly type in the chat, what is the minimum frequency that is required for the ejection of electrons. So this is the energy that we are giving. Yes, that is the threshold frequency, which will be known as h nu naught. So whatever energy I am providing, first this much energy, it will be used for the ejection of electron. Now, let's suppose if we are left with the extra energy, that will be used for increasing the speed of the electron, which is basically the kinetic energy of the electron, right? And kinetic energy is equals to, which you have learned in physics, that is equals to half mv square. Omkar, that is not 10. That was just an example, right? Just an example which with which I said you, okay, let's suppose if we require 10, right, electron volt, and the energy that I'm providing is 15 electron volt, then obviously 10 will be used for ejection of electron and 5 will be used for increasing the speed of the electrons. So this was the other formula that we have got. How is the energy that I am providing and the threshold frequency, or I say threshold energy, or this is known as the work function. This is known as the work function. This is known as work function, or we say it as the threshold energy. And this mu naught, it is known as threshold frequency. So this is what the picture looks like. That is, we are right now on learning about the developments that lead to the Bohr's atomic model. And in that now, by now we have got three formulas, which is the speed of light is equals to nu into lambda. Then we have got the formula for energy, and this is the formula how I relate the energy, threshold energy, and the kinetic energy of electrons that are emitted in whenever I put some light on the metal surface. So basically what is happening here is that instead you should imagine it like this. You should imagine it like this, that some photons, ball kind of a things are coming, they're striking, they're colliding with these electrons, and if the energy is sufficient, if the energy is what the electron requires to come out, then it will transfer its energy, and then the electron will come out of this surface. So of course, these formulas, they are very, very important for us. But the very important part is once you remember or memorize the formulas, the important part is the unit conversion. So here what you will see is that sometimes your work function, it will be given in electron volt. It will be given in electron volt. Now, the only thing that is remaining is how do I go from electron volt to joule? Because what you have is you have the Planck's constant in joule second, right? So usually the unit that will be used for specifying the energy is joule. So now the next step is you should know how do I go from electron volt to joule. So what's the relationship between electron volt and joule? Yes, what's the relationship between the electron volt and joule? And this is the work function of different metals. This is the work function of the different metals. For lithium it is 2.42, for sodium it is 2.3, and for potassium it is 2.25, magnesium 3.7, copper 4.8, and Ag 4.3. And there is a table that is given to you in NCRT also, and this is the question that you have got last year in JEE, where it was asking, it gave you the value of the work function for the few metals, and then what the question that they have put is you have to tell the number of metals which will show photoelectric effect when the light of wavelength 400 nanometer falls on it. It is. So yes, of course, every year you get one question from photoelectric effect, which might be based on work function, or else it will be based on finding out the kinetic energy, or the threshold frequency, right? So what you will be given is you will be given the energy, and then you have to do your calculations. What you have to do, so you can note down, you can take the screenshot, you will have to solve this, and then when we are solving the numericals, then we'll see what's the answer. right? Or how do we solve it? So first you have to try it, and then of course we will solve this. Okay, so Omkar is asking, which formula do I use to calculate this? So what I said is that there is some minimum energy that will be required for the ejection of electrons from the metal surface, right? Now what they are saying is, read the question very carefully. Number of metals which will show photoelectric effect when light of wavelengths. So the wavelength of this light which is falling is 400 nanometer. Now what we will have to do is, we will check that the energy. So if the wave has this wavelength, then what is the energy that this wavelength is coming with? Can I calculate the energy for a wave which has the frequency, which has the wavelength of 400 nanometer? Is it possible? Yes, Omkar. Is it possible to calculate the energy for the wave or the radiation of the wavelength 400 nanometer? Yes. So yes, let's suppose the energy is, so this the energy that is coming out, that is, that we are providing, which is h nu, correct? Now I have the work function, I have the work function. And how do we define the work function? We define work function as the minimum energy that is required for the ejection of electrons. So now I have the minimum energy. So lithium requires this much energy and sodium requires this much energy, and so on for other metals. So now you know what is the minimum energy that lithium requires for the ejection of electron. Correct? Now what you do is, whatever energy you have calculated, convert it into electron volt and then compare it with these work function. So if the energy that is coming with this wave, let's suppose the energy is something 3 electron volt. Now compare it. So energy that is coming is 3 electron volt, and the threshold energy for lithium is 2.42, right? So yes, it is lesser than 3 electron volt. So of course the electrons will be ejected, right? Because the energy that is required for the ejection of electron is 2.42 electron volt, which is lesser than 3 electron volts. So what will happen? This much energy will be used for ejection of electron, and rest of it will be used for the increasing the speed of electrons. That will be used for increasing the speed of electron. So this is the total energy. This is, so let's take for lithium, this is 2.42, which is the minimum threshold energy, or we say this is the work function, right? And along with that, I have the kinetic energy. So whatever is left, that will be used for increasing the speed of electron. So you can calculate it, right? So what is the energy that will be left here? So what you will have? 0.58. What you will have? You will have 0.58. So basically 0.58 electron volt goes for increasing the energy. Have you understood this? How you have to approach this question? What they gave here is, they gave you the minimum energy. So now you just have to find what is the energy that is coming. Okay. And if the energy that is coming, it is more than the threshold energy, then obviously the electrons will be ejected. If it is more less than the threshold energy, then obviously we don't have the sufficient energy for the ejection of electrons. So let's suppose it is 3 electron volt, that is the energy that is coming. So now let's compare. So 3.7 is more than 3 electron volt, correct? So yes, there is no ejection of electron for this. Again, 4.8 is also more than 3 electron volt. So here also electron will not be ejected. And for silver also, there is no ejection of electrons. So this is the question which is based directly out of NCRT. So yes, your questions will be based out of NCRT. So make sure that you are solving all the questions which is there in your textbook. because the questions, they are directly based out of the questions from NCERT. I'll show you other questions also which have directly come from NCERT, basically from the exercise and the solved numericals that are there in the NCERT. The only thing that will change is they'll just change the language or the numeric values that are there, but the concept remains the same. And also the other thing that will remain same is that the topic from which they are giving the question. So every year you are getting question from the photoelectric effect, or I say that every year you get the question from this topic, which is will be based on where you are supposed to use this formulas. So for you, just take a sheet, note down the formulas like this, and you should know where and when I have to use the particular formulas, because as we will proceed there will be lot many formulas that you will come across, so you should know where and when I have to use the particular formula. So this you can take the screenshot and you will have to solve this question. So first what you have to do is, using this wavelength which is 400 nanometer, calculate the energy that is coming. If the energy that is coming, it is more than the threshold energy, then obviously there will be the ejection of electrons. So will you be able to do that? If you will be able to do that, quickly type yes in the chat, and then we will wrap this all up. So this is what we have done till now. Now in the next class, we have to start with learning about the spectra. What we have to start, we'll be learning about the spectra. So basically we will be learning that your spectra looks something like this. This is the absorption spectra and this is the emission spectra. This is the absorption spectra and the other one is emission spectra. Why we are calling it as spectra? Because yes, if I take all the colors, then we have read like electromagnetic spectrum. So one wavelength which is put after the other wavelength, then we have the third, fourth, and so on. We get the band. Basically, spectra is the word for band, right? So here we are getting a band in which, yes, of course, there are certain colors which are missing, and here what we see, certain colors are present here, right? We are just getting the lines respective to certain colors, whereas in the absorption spectra what I can see is that certain colors are missing. So what I can say here is, this is like a photographic negative of this. If I'll overlap both of these, then I'll get the complete spectra, right? So then now we will understand why these lines are missing. Why, if I'm taking the emission spectra, why we have certain lines? Why don't we have lines for all the colors? Why I'm not having the line for yellow color here? Why I'm not having the line for other colors, right? Orange or some other color, or violet color. Yes, for violet we have, if you will see closely, we have two lines for the violet. So these all things we'll have to answer, right? Why the spectrum looks like this? Why is the spectra looking like this? So all these, they will be questions will be answered when we consider light as a particle. And then we'll see like how do I get the absorption spectrum and how do I get the emission spectrum. So there are two kinds of spectrum. One is the absorption, another one is the emission spectrum. And then finally we will continue with the emission spectrum for hydrogen atom. And there also we will see the formulas. How do I give the value of these lines and how do I calculate what is the number of lines that I see for the particular atom. So in our next class, we'll be learning about the atomic spectra. So if you find time, just give a quick reading, be ready with your doubts so that you have a better understanding of whatever we are learning in the class. So all who are new to this, so this was a quick revision for all of you. So what you do is just go through the previous sessions or just go through these topics, and then yes, you can start with the topic that we will be learning tomorrow, which is the atomic spectra. And this is a very important portion of chemistry that we are learning right now, because here we are learning about the atom and how does the structure of atom evolved over the years. And once we are done with the atomic spectra, then finally we will learn about the Bohr's atomic model. So I hope this is all clear to this all is clear to everyone. So if this is, then quickly type yes, and then we will end this session. So are you all ready for tomorrow to learn about the atomic spectra? Are you excited to learn about the atomic spectra? Yes. So yes, the atomic spectra is very interesting, right? This is a very, very interesting topic. So we'll be learning about what's the difference between absorption, emission, and then yes, this is basically what you see here is the atomic spectra for hydrogen, right? That's the easiest one to study and less complicated. So what we will be learning, this is basically the line spectra for, there are lines, right? So yes, these are also known as the line spectra. So this is basically the line spectra for hydrogen. So we'll be learning all these things, and be ready, revise all the things, do the numerical that I gave you today based on whatever we have revised. I hope all of you can at least solve all of this. What you have to do is the formulas that we saw just now. So you can just take a screenshot and just you have to put the values. Everything is here, whatever we have learned till now, this is, or everything is here on just one screen. Okay, this is all we have learned till now, and these are the formulas that we have been through. Okay, so this is all for today, and then I'll see you in the next class, which is tomorrow. Yes, ma'am.
Yes, ma'am. Thank you, ma'am. Students, we have a small announcement. I invite Arun sir to do the announcement.
Thank you, ma'am. Students, scholarship exam, third phase out on the 28th of this month. New students can also apply. New students apply చేయొచ్చు as you have secured the seat. కొత్త స్టూడెంట్స్ కూడా అప్లై చేసి సీట్ సెక్యూర్ చేయొచ్చు. ఆల్రైట్, 28th కి ఎగ్జామ్ ఉంది, థర్డ్ ఫేజ్ ఉంది. సో ఫస్ట్ ఫేజ్ యూఆర్ సెలెక్టెడ్ 20, నెక్స్ట్ యూఆర్ సెలెక్టెడ్ వీఆర్ టోటలింగ్ ఇట్ టు 100 స్టూడెంట్స్ ఉంటారు టోటల్. సో నెక్స్ట్ ఫేజ్ 28th కి ఉంది, కొత్త స్టూడెంట్స్ అప్లై చేయొచ్చు. Please forward this message to all those possible contacts you have got. School groups ఉన్నాయి, friends group ఉన్నారు. All right, so that they also get to know that there is a free scholarship, free coaching available. So let them know so that they also can get the advantage of free coaching. All right. Thank you all students. Thank you, ma'am.
Yes, sir. Yes, sir, students. Those who have written the latest exam. ఓకే, మీకు ఏంటంటే ఇప్పుడు మెటీరియల్ కావాలి అంటే యూ హ్యావ్ టు డూ అ సెక్యూరిటీ డిపాజిట్ ఆఫ్ 5,000 రూపీస్. మెటీరియల్స్ ఆర్ ఫర్ ఫ్రీ, but you have to do a security deposit of 5,000 rupees, which is refundable after 2 years. Okay, so those who have not done, not the old students, it is to all the new students. Already old students have paid and they have taken the material. They have done the security deposit and also taken the material by post. Just a second. Yes, for new students to apply Omkar mali register chesukodaniki exam ki same link. You can forward to your friends. So material by post పంపిస్తాము. So the materials are for free as we said, but we need a security deposit of 5,000 rupees. And you can do a security deposit of 5,000 rupees to the number 96422. Just a second. 9642215228. ఈ నంబర్ కి సెక్యూరిటీ డిపాజిట్ ఆఫ్ 5,000 చేసి స్క్రీన్ షాట్ పంపిస్తే అప్పుడు మేము మీకు బుక్స్ పోస్ట్ చేస్తాం. ఓకే, ఇట్ ఈస్ రిఫండబుల్ ఆఫ్టర్ 2 years and the books are compulsory, right? So again we will meet in the evening 7 to 9.